Hi there, welcome to part 2 of how to measure graphene using the Edinburgh Instruments RM5 confocal Raman microscope. In part 1, we showed you how to load graphene under the microscope, configure your system for analysing the material, and understand its properties through its Raman spectrum. In part 2, we're going to show you how to image the various properties of graphene by tracking changes in its Raman spectrum across a sample. Let's get into it. So in part 1, we covered lining the graphene under the microscope, which I did here using Microscope setup window, and then running spectral measurements using the Raman measurement window. Also, we covered how to calibrate the system, which can be done here. So all of that's done. We'll skip over that, and we'll go straight to mapping. So to take a map, we'll go to this button here that says Raman Map. The first window in the Create New Map setup is basically just making your microscope image, and we showed you how to do that earlier. So I'll go on Grid, and now what I'll do is I'll draw a box over an area on this image, and this will basically define the mapping area. So we'll create a Raman map between here and here. To define the resolution of this mapping area, we can either set the spacing or the number of points. So if I were to enter 20 by 20 points, we have 2.33 by 1.96 micron spacing in X and Y. But let's be a little bit more accurate, and we'll do a 1 by 1 image. So that'll be 45 by 38 pixels. Now I'll click on measurement parameters. So I defined all of these in part 1. Before we start our map, we'll run a spectrum just to sense check everything. So I'll just go into the middle of the mapping area and I'll click Start. So this is a very nice spectrum so we did this over 0.2 seconds. So let's look at the different bands that we have in it. So this band here is just a phonon mode of silicon that's underneath the graphene, so we can ignore that, that's not important. This peak here at about 1350 is the D band. So if there's any defective areas, we should see an increase in that signal. This here is the G band at about 1590. And then here we have the 2D band at 2700. So we can map the intensities, peak positions, widths of all of these bands in a single shot, which is great. Because our exposure time is 0.2 seconds, we can apply fast mapping. So we've went from about 14 minutes down to just under 6. So to start the map, I'll just click Start Map, turn off the light. Yep, already done. Let's run our map. Okay, so now our map is running. We can track the intensity of any band we choose. So this yellow rectangle will show the intensity over which this image is being integrated. So we have the 2D band being tracked. We can track the G band, and that will change, yep. And then we can also track the D band. So we're seeing different things, which is good. But it doesn't really matter what you track at this stage, because you can create any map analysis you want when it's finished. So our map's finished running. Let's analyze it and see what's going on the sample. So if I click on any point in the sample, I can see the corresponding spectrum at that point. Our peak intensity is focused on the G band, so let's change the name of this analysis to IG. It appears that quite a lot's changing. Let's first do some processing to get the spectrum looking the way we want. So we'll first crop out the silicon band. We can do a background subtraction. This will account for any fluorescence effects that might alter peak ratios artificially. Brilliant. And let's smooth as well, because our lower intensity spectra are a bit noisy in the baseline. So if we smooth, we can just get rid of that. Okay, so there are various things that we could track using this Raman map. We could do peak ratios to get a better idea of the layer number across the sample. We could take the peak intensity or area of the D band to work out if there's any areas of higher defect density. We can also take peak positions of our G and 2D bands to work out if there's effects like strain going on as well. Let's do peak ratios first to work out layer number. So to do this, we need to first take the peak intensity of the G band, which we already have. Let's also take the intensity of the 2D band. We'll call that I2D. And so we can visualize it a bit better and we'll give it a different color. Okay. So now let's take the ratio of these two bands, and I'll explain in a minute how this gives us information about layer number. So let's give that on a turbo. We'll make sure they're in the right order. So the convention usually is to do the 2D band divided by G band. Excellent. So we have a lot of variation in the peak ratio here. Call that I2D over IG. That's better. So red corresponds to a large I2D over IG, which means that the 2D band is much more intense than the G band. This is characteristic of monolayer graphene. So if you were to take just pure monolayer and run a Raman spectrum, you'd most likely see that the G band was less intense than the 2D band. In these green-yellow areas, they're a bit closer to having a ratio of 1. So it's probably approaching bilayer. And then as we go into dark blue, the G band is much more intense than the 2D band. So as the number of graphene layers increases and basically gets closer to bulk graphite, you'll start to see this band get much larger than this one. So what we're seeing in these blue areas is multi-layer graphene, probably tri-layer. So that's layer number. Let's have a look at defect density. So to take that parameter, we'll look at the peak area. And what we'll do is we'll zoom in to where we know the D band is. So about here. Change the color again. Okay, so this is area D. So we're seeing it's quite uniform, but we're seeing discrete bright spots which correspond to increased D band intensity. So if I go to pink again, it's very low, and if I go to yellow, it's much larger. So what we're able to see here is that there's areas of quite high defect density across the sample. So the sample's not perfect. It could be due to mechanical errors in the graphene. It could be errors in the underlying silicon, which is affecting the graphene. It could be dust that's on the sample. Finally, let's look for effects like strain. So to do that, we generally track the peak position of a band. So as your material becomes strained, the position of the band will change to represent the changing vibrational properties as the material becomes stretched or compressed. So I'll just click peak position. So the position of the G band is now shown in pink. We'll change that, let's put it as rainbow, and we'll call this peak position G. So what we see is quite a big change across our sample. So these areas in blue and purple show you a lower Raman shift, and then and red, for example, the Raman shift's increasing. So this could be due to the layer number changing, but for example, if you have areas that are clearly the same layer number through this image, but the peak position is changing, then you could conclude that there's strain occurring in your sample. All of the data properties, so your metadata, is included in the Ramacle file. So you can get this later if you need it for reports or publications. If you're finished processing at this point, you can just save the data. So you click File, Save As, and then you can save it as a Ramacle file, CSV, for export to things like Python or MATLAB. There you have it. We've covered Raman mapping of graphene. We've shown that we can track changes in layer number, defect density, peak positions to track things like strain, all within a matter of minutes. If there's any materials that you'd like to see covered next, please let us know in the comments. To stay up to date with videos on Raman fluorescence, please subscribe to our channel.